Today I would like to discuss the topic of water on the moon and then go on to discuss some of the planned human missions to the moon. This is a nice picture of Shackleton Crater. Shackleton Crater is in the moon's south pole. It's 21 kilometers or 13 miles in diameter and has a depth of 4 kilometers or 2.5 miles. This crater is interesting since its floor is always in darkness. In this image, the right side is the same picture of Shackleton Crater from earlier, but the left side is colored according to elevation. The redder colors are higher elevations and the bluer colors are lower elevations. You will notice the nice bowl shape to the crater. Here's a diagram of the Earth and the Moon we saw in an earlier lecture. This time, let's particularly focus on the orientation of the Moon. I already mentioned that the orbital plane of the Moon is inclined by about 5 degrees relative to the Earth's orbital plane around the Sun. The latter is usually called the ecliptic plane. Even factoring that in, the Moon's poles are nearly perpendicular to the ecliptic plane. It's slightly off in that the difference is about 1.5 degrees, but it is nearly perpendicular to the direction of the Sun. What this means is that if you were inside a large crater located either on the north or south pole of the Moon, you would never see sunlight. This is why the floor of Shackleton Crater is permanently shadowed. In this video, Shackleton Crater is in the center. What you will notice is that as the Moon orbits the Earth, different parts of the Moon receive sunlight. However, the floors of certain craters, such as Shackleton Crater, never get sunlight. That is to say, they are permanently shadowed. Not receiving any sunlight means that floors of certain craters are very cold. This image shows temperatures during the time when these regions of the Moon have the potential to get sunlight. Notice that these are the highest temperatures that these regions experience. Purple-blue colors are temperatures between 25 to 100 Kelvin, so many of the permanently shadowed regions consistently have temperatures below 100 Kelvin. Note that 100 Kelvin is minus 279.67 degrees Fahrenheit, or minus 173.15 degrees Celsius. For reference, you are probably aware that water freezes at 0 degrees Celsius or 32 degrees Fahrenheit, or equivalently 273.15 Kelvin. Speaking of water, it is very important for life and for future space exploration. Not only is water useful for consumption, but it can be broken down into hydrogen and oxygen through a process called electrolysis. The oxygen can then be used for breathing, or both oxygen and hydrogen can be used as rocket propellants. Let's take a closer look at electrolysis of water. As you probably know, water consists of two hydrogen atoms bonded to an oxygen atom. While you can assemble water by combining hydrogen and oxygen, you can also go in the reverse direction and break down water back into hydrogen and oxygen. On the right is an example electrolysis setup. In the setup is a tank of water that is separated by a membrane that allows hydrogen ions to pass through. When electrons flow down the negative terminal, they combine with hydrogen ions to form hydrogen molecules. Those hydrogen molecule bubbles can then be collected from the top as shown by the green arrow. On the other side of the membrane, water molecules break up into oxygen molecules, hydrogen ions, and electrons. Electrons are attracted to the positive terminal, while hydrogen ions pass through the membrane to the other side. Oxygen molecules are then free to rise as bubbles to the surface and can be collected as shown by the purple arrow. This is a straightforward process that can be implemented, for instance, on the Moon if there is an electrical power source which can be provided by solar panels. Let's pick up the story of water on the Moon with the Lunar Prospector mission. It was a NASA mission that was operational between January 1998 and July 1999. Lunar Prospector carried a neutron spectrometer that could detect hydrogen on the surface of the Moon. In the video, you can see areas of the Moon's south pole shown in blue for where hydrogen is present. It should be noted that this only tells us that there is hydrogen at the poles of the Moon. This may mean that there is water, but it doesn't have to mean that. About a decade later, the Indian Space Research Organization, ISRO, launched the Chandrayaan-1 mission to the Moon. It was operational between October 2008 and August 2009. One of Chandrayaan's instruments was the Moon Mineralogy Mapper. Using data from this instrument, scientists have identified areas of the Moon where water ice is present. Those areas are shown in the image using teal-colored dots. On the left is the South Pole and on the right is the North Pole. Note that Shackleton Crater seems to have water ice in its interior. I would like to pause for a bit to consider how spacecraft instruments identify material on the surface of a planet from orbit. Spacecraft typically detect one or more types of light, or more specifically, electromagnetic waves. You probably know there are different types of electromagnetic waves ranging from radio waves to gamma rays. Another thing to note is that depending on an object's temperature, that object emits mostly certain types of electromagnetic waves. The surface of the Sun, for example, is about 6,000 Kelvin, so it emits most of its electromagnetic waves as visible light. Speaking of sunlight, if you look closely at light emitted by the Sun, you will notice an interesting pattern. As you know, sunlight can be broken down into its rainbow of colors. colors, using a prism, for example. In this image, sunlight can be separated into its spectrum of colors. From left to right, the frequency of light increases and then it continues on the next line. Notice that there are certain spots where the typical red, orange, yellow, green, blue, purple spectrum is missing colors. This is not for the lack of data. That's how the actual solar spectrum looks like. What is happening is that as sunlight passes through the sun's atmosphere, the atmosphere absorbs specific frequencies of light based on the composition of the atmosphere. As such, by looking at which frequencies of light are missing and comparing them to a database of known frequencies of certain elements, we can figure out the composition of the sun's atmosphere. This is similar to what is done with surfaces of planets to identify compositions of their surfaces. Next, let's look at the Lunar Reconnaissance Orbiter, which is a NASA mission that has been operational since June 2009. Much like the Lunar Prospector mission, the Lunar Reconnaissance Orbiter detected hydrogen at the poles of the moon by measuring neutrons. Recently, scientists have found higher concentrations of water in Apollo samples. Specifically, Apollo 17 astronauts found orange soil as shown in the picture on the right. If you look at that soil using a microscope, as shown in the image on the left, you will see small orange glass beads. These beads were produced as volcanic material cooled very quickly. Since these beads solidified quickly, they are ideal for trapping any water that was present at the time. Next, let's look at LADEE, or the Lunar Atmosphere and Dust Environment Explorer. LADEE was a NASA mission that was operational between September 2013 and April 2014. One of the discoveries of the LADEE mission was water that is released from depth as a result of small impacts. Small impacts may strike the surface and produce debris, but more energetic impacts penetrate further down and excavate material that has more water. LADEE was able to detect that water. How much water are we talking about? The LADEE mission's estimate is between 200 to 500 parts per million. What does that mean? Let's say you wanted to produce 500 milliliters of water from lunar soil. A small water bottle is shown on the left and some lunar soil is shown in the middle. The question is, how much lunar soil would you need? If there was 500 parts per million water in the soil, then you'd need to process 1,000 kilograms, or roughly the same mass as a small car, to fill your bottle of water. How did the moon get water? One way may be the result of solar wind. The sun produces protons that constantly shoot out from it. A hydrogen atom is essentially a proton and an electron. As such, if protons shot off by the sun combined with oxygen on the surface of the moon, that could produce water molecules. Now, it isn't crazy to think that oxygen is present on the surface of the moon. Many rocky material have oxygen, so it is possible that this mechanism helped produce water on the moon. Another more straightforward method is water being delivered to the moon by comets. In the image above, you will see a tail of a comet. Tails of comets are partly produced by water ice that is sublimating. Now let's briefly consider some of the plans for future human exploration of the moon. Let's start with NASA. NASA's current plan for future human exploration of the moon is called Artemis. The plan is to land humans on the moon by 2024. The Artemis program relies heavily on a new rocket that is in development. The Space Launch System, much like the Saturn series of rockets, is a series of rockets that will be developed over time. There will be a crew version to carry astronauts and a cargo version to carry equipment and supplies. Over time, there will be improved versions for each, culminating with the Block 2 designs. Looking at the heights of these rockets, you can see that they are in the scale of the Saturn V rocket, which had a height of 363 feet. The Space Launch System uses technology developed as part of the Space Shuttle program. That is why these rockets look more like the Space Shuttle than the Saturn V. The Artemis program is similar to the now cancelled Constellation program from the mid-2000s. There, the plan was to land humans on the moon by 2020. The Constellation program also called for two rockets, the Ares 1 to carry astronauts and the Ares 5 to carry cargo. While the Ares 1 was fully cancelled, the Ares 5 lives on in some ways as the Space Launch System. Moving to the Russian space agency, Roscosmos, their plan is to land humans on the moon by 2030. Shown on the right is their Ariel spacecraft that is in development to replace their Soyuz spacecraft. The China National Space Administration is planning on putting humans on the moon by the 2030s. I couldn't find a specific spacecraft in development for going to the moon, so shown on the right is a drawing of their current Shenzhou spacecraft. Much like the United States and Russia, China is also developing a large rocket to send humans to the moon. This diagram compares the Super Heavy Lift launch vehicles, which are rockets that can put at least 50 metric tons or 110,000 pounds into low Earth orbit, or LEO. We have already seen the Saturn V and the N1 rockets. To the left and right of them are the Space Launch System, or SLS rockets. To the left of the SLS Block 1 rocket is the Long March March 9 rocket that China is developing. A unique idea of exploring the moon is the hashtag Dear Moon project. The idea with this mission is to take a group of artists on a free return trajectory around the moon so that they would be inspired to create new art based on their experiences. The current plan is to fly this mission in 2023 using a SpaceX Starship rocket.